Okay, let's talk about the background. The background includes some knowledge or information which are important to understand the development of the models or measures or the tools later, right? But we don't go into very details on those background information, but we need to keep those in mind. So for 421 student, so you will see some familiar pictures I used before. I only picked the most important ones about this course. This is the same picture I showed before in 421. I couldn't find new data, but this should be good enough to give you the big picture about the trend of the energy resources in the US utilized for generating electricity from 1950 until 2023. Okay, so I use different colors. So brown color means a coal-fired power plant. Blue means natural gas. Red means nuclear. Green means renewable. And also there's some other like oil or some other fossil generators. So this pie chart indicate the distribution among some major resources in 2023. So by 2023, the natural gas is actually the largest one. It takes more than 42% to generate electricity. And second one is actually nuclear. And third one is coal. And all the renewables. So when we say renewables, we usually don't consider hydro. And that's about 70%. If you also add hydro to renewable, that totally is 23%. So that's what happened at the end of this trend, right? But over long time, the coal-fired plant has been the major resource of electricity generation. So I still clearly remember around this time, like 2009 or 8, and there's many projects talking about how to retire. When I work for EPRI, there are many projects talking about how to retire coal-fired power plant. There's a lot of reliability issues because when you retire a coal-fired power plant, you also lose the control there in that area. So when you build a natural gas power plant at some other locations, your system will lose some controllability in one area and maybe add some new controllability some other area. So they want to make sure that won't cause some reliability or stability problem. Some coal-fired power plant, after they retire, they just keep that plant there as a control device called a synchronous condenser. We can talk about that one in the voltage control session. But starting from about 2008 or 9, you see the coal-fired power plant is actually retiring. And that is pretty much increase supported by a natural gas power plant. And nuclear stay about the same for a long time. But I envision quickly that you will see grow quickly. It can grow in the next 5 to 10 years. One reason is there are a lot of data centers, right, going to be connected to the grid. I think the Tesla announced there's the first like 1 gigawatt data center, hyper data center that consume 1 gigawatt power only just for one facility. The 1 gigawatt power is equivalent to one large power plant. Okay, and the U.S. Predict in the next 5 to 10 years, there will be there will be about 50 to 100 new power plants to be built in order to support those data centers. But nuclear power plant will take usually 7 to even 7 years or longer to build. So nuclear power plant is ideal for data center. It's very reliable, but there will be a lot of challenges to build so many nuclear power plant. But anyways, there will be, I guess there will be increase of the percentage for nuclear in the next few years. Renewable, including wind and solar. So that has very clear trend to grow, but based on the current administration, so that one, the growing will happen, but it will be slow, or can be slowed down. I don't know. So I also personally looking forward to any new data about the change on the energy resource in next 5 years. But natural gas will be still the number one, right? Nuclear number two, and coal-fired power plant number three for the energy resources to generate electricity in the U.S. Okay, so this picture tell where the load is, right? So you can see for the East Coast, because there are a lot of large city or people based on the population, so the load there is higher and dense. And for the West Coast, so in the large area, the load is much lower. And the second figure is just show where the electricity is generated by so the types of the generators are showed by different color. For instance, black or gray color indicate coal. Nuclear is red, and natural gas here is brown, and wind is green, and yellow color means solar. Okay, so this generation map basically match the load map. So basically tell where we need to build more generation to support the load, because it's not economical to deliver electricity over very long distance. You always need to reduce the delivery cost from the generator to the load. Then we need a power grid. So this is the topology of the power grid in the US. So it use different colors to indicate different voltages. But if you don't look into the detailed color, you can still see there's a very dense power grid in the East Coast. And on the West Coast, and the grid is sparse, and also in pretty large area, there's not much facility there, such as Nevada State. So we're going to utilize the grid to deliver the generative power to the load. Okay, so next few slides, we talk about the some issues with integration of the renewables. We start from the wind power as an example. For the wind generation, in the middle west area, right, there's a very rich wind resources. So which means if you build wind farms, you can generate a lot of electricity. And some other area you can build which is ideal to build wind farms, such as like northeast or near the coast. But if you remember where the users are in the country, right? So they stay in large city area. In order to utilize the electricity generated by wind, you need to build long transmission. So just indicate as the white arrow. So you need to deliver electricity from the center of the wind generation to the city areas. So there's a mismatch which is geographical mismatch, because you want to move the energy from one area to another area. Another figure is talk about another type of mismatch between mismatch in time. So there are bar chart indicate the demand. So those value actually the demand for each hour. Like we pick one example, like for example, we use summer demand. Summer demand will be those orange color, right? So if you find those orange bars, the load become the highest around the time from 17 o'clock to 18 o'clock, from 5 to 6 p.m. So that's the peak hours. The load will be the maximal. The load become minimal around 3 to 4 p.m. So 3 to 4 a.m. in the early morning. The load is minimal because people are still sleeping. So the curve, a typical load curve over 24 hours will be like this one. Okay, so that's a summer demand. If we also check the wind generation or the wind resource in summer, so that is the green curve. That is the green curve. So that curve become a maximal in early morning, around 3 to 4 a.m. But when we need a lot of electricity around 5 and 6 p.m., the wind becomes smallest. Okay, so which means if you know this curve and you know the total energy you need to provide as a power company to your users, what you need to do is you integrate the curve, right? So for the load curve, you just calculate total area under this load curve. That total area tells you total energy you need to generate every day. Then you can assume, okay, how about I generate all electricity by wind? Then you find this green curve. You integrate the area under the green curve. You also get another number. So by comparing those two areas, they're pretty similar, right? So which means by only checking the mass, maybe one number is roughly the same as another number. As planner, you can say, okay, so I have enough wind generation, which is to power my customer. But your engineer will say no, because you think there's a mismatch, right? But early morning, you generate more electricity than the demand. But in the early afternoon, you don't have enough generation. So that is some reliability concern. So you want to expect you have some other power plant in the early morning. Definitely you don't use those power plant, but in the late afternoon when the wind generation is lower than demand, you need to pick up those power plant. You can quickly just start those power plant to generate electricity. So this one give you an example. Even you have built enough renewables, such as like wind power plant, wind farms, which is enough for your load in terms of total number. There still be mismatch, temporary mismatch. So now we consider like a geographical mismatch and also temporary mismatch. The both mismatches will cause some reliability problem. Another example about the solar. So each curve here is also the load curve, but it looks very different from the previous one because this curve is for California. California has a lot of rooftop photovoltaic solar panel, which means for any user, you install those solar panel on your rooftop, and some of electricity will be generated by that panel, not by the power company. But from the power company side, they may think, okay, so those solar panels take some burden of our generation, but actually they can introduce a reliability problem because the load curve they can find will be like this curve. It's very different from the curve they have been familiar with. This area is generated by the photovoltaic on the rooftop by the end user, not by the power company. Definitely the power company need to generate much less energy, but they are going to face some reliability challenge. The one challenge is you see at this time around the sunrise. So the generation from the solar power will suddenly quickly go up. So their load curve will go down. And around the times of the sunset, and you see the generation of solar will go down, and their generation from power company need to go up. So the power company need to deal with very large ramp up of more than 10 gigawatt in 3 hours. If you're familiar with how quickly conventional generator can pick up the load, can go increase the generation, this speed is much higher than even the fastest unit, like gas turbine generator. So they face a lot of challenge. Okay, even they generate less energy, but they need to deal with this flexibility when the solar power is growing or decaying. So this curve is called dark curve or dark chart, which is pretty famous examples. Okay. Right. So let's summarize some reliability challenges with integration of renewable. Okay. The first one is the electricity demand and wind generation of a power system has geographical and temporal mismatches, which need to be addressed by building long transmission or maybe add some energy storage to compensate the mismatch. The second, the power system with high solar penetration may face a risk of a daily oversupply with too short, steep ramps each day around the sunrise and sunset. So this is referring to the dark curve problem. Both solar and wind actually will bring some challenge for the short-term forecasting because the short-term forecasting of the wind generation and solar generation are still not very accurate. And wind, solar, and other resources, if they're connected through power electronics inverter, they may not provide inertia. They don't behave as conventional generator has revolving rotor. That revolving rotor may be a bad thing for efficiency, but actually they slow down any dynamics because this course will focus on dealing with contingencies of normal conditions. If something happens, we want the dynamics can be slowed down. But when you retire some conventional generators and use wind and solar and other resources, the inertia will be reduced. That will impact both frequency and voltage. And also to maintain the grid reliability, the renewable energy is not free. It's not like a simple math. You have a total generation equals total load. You still need to pay extra price for example, to upgrade your transmission network to prevent congestion. If you don't have enough transmission lines to deliver generation from a wind farm to the users, you need to build more transmission lines. You also need to maintain spending reserve. Spending reserve means some generators, typically they are conventional generator, like a gas turbine generator. They are not renewable, but they have to keep running all the time. So for instance, if for the California, so starting at 3 or 4 p.m., you need to quickly pick up those gas turbine generator. So they will be running all the time there to be prepared. Okay, the last one. So you may need to install the energy storage, such as batteries, and also you may want to upgrade your inverters or power electronic controllers for grid support. But in order to do that, you have to understand what can happen on the grid side. So you need to have good model and also the methods to study the stability of the grid. Okay, so this is the last slide for the first lecture. So I will see everyone on Friday to continue.